every time we look out with the standard model, we see something that makes perfect sense, that we go, yeah, that's exactly what we expected to see. And that happens a lot. A lot of the time, astronomers go out and find what they're looking for. So I have a couple astronomers talking over some of the really cool findings that we totally predicted.
Let's say you're looking at a galaxy and you're looking at the motions of stars in that galaxy. You're looking at the speed of their orbits, and something's wrong. The stars are moving too fast. You have two conclusions that you can reach. Either we're missing mass in the universe. Either there's something in the galaxy, there's some sort of mass, whether it's something that doesn't glow, that doesn't interact with light, and that's what's keeping the galaxy together. The second conclusion you can possibly have, the option, is that maybe the laws of physics are wrong. Maybe we don't understand gravity. Maybe Newton and Einstein aren't enough to explain the motions of stars at galactic scales. One hypothesis, the dark matter hypothesis, is able to explain all these observations. And that's really the strength of modern cosmology. That's why we tend to believe the things that we believe. It's not just one piece of evidence, it's not just one line, but multiple lines that all point in the same direction. Mother Nature is trying to tell us something here. And that something is, hey, by the way, it looks like most of the mass of the universe does not interact with light.
I'm Jana Levin, and I'm a professor of physics and astronomy at Barnard College and Columbia University, and I primarily study astrophysics. And in physics, there's kind of a distinction in people who work in physics between experimentalists, observers, and theorists. Theorists, such as myself, use the mathematics to try to make discoveries, to talk to the observers, and maybe make suggestions for what they could look for. So sometimes there are discoveries made with telescopes that we just didn't foresee, and then we have to go back to our pen and paper, back to the drawing board, and figure out what did we miss and how could we not have predicted this phenomenon. And often it goes that way, that we're trying to understand something we've seen in the world but don't yet understand. But there's a real conversation between doing the math, making a prediction, going to the observers to make an actual observation.
This is my take on this. This is the equation that we know is right. This is sort of the bedrock of our understanding. But although we know it's right, there's an awful lot in this equation that we haven't understood. There's an awful lot, to me, that's still mysterious in this equation. So my response is, I think that maybe we should just go back to the drawing board and start to challenge some of the assumptions and paradigms that we've been holding for the past 30 years. So I should admit, I feel quite energized, actually, by the lack of results for the LHC. You know, it feels good to me that everyone was wrong. You know, it's when we're wrong that we start to make progress.